Today we're going to talk about the ratio and root test. So for the ratio test, let's start with that one. So ratio test. And these are tests for convergence. So how does this one work? And the ratio test will be extremely important. So very, very important to get this one right. So we're gonna define. So let row. We're gonna start with a series as usual. Our series will be the sum of the a n's. I'm gonna do row as the limit as n goes to infinity of a n plus 1 over a n. And we're not gonna care about the sign of this, so that. And we're gonna have three possibilities. One, that row be between 0 and could be equal to 0, row, and not 1. 1, we don't know what happens. In this case, when you compute your limit, you end up with row between 0 and 1. Then this tells you that your series, funky sum there, converges absolutely. So it's not only a convergence test, but also for absolute convergence. So at row equals to 1, well, the test is not conclusive. So we don't know. So at that point, we have to analyze the situation in a different way. And now if rho happens to be strictly greater than 1, then the series diverges, period. So that number 2, what can happen is that at rho equals 1, you could have that the series converges, but only conditionally. It could also converge absolutely, but it may not give you that the ratio test is conclusive. It's just you don't know. And it could also diverge. So anything can happen on that situation. So let's take a look at a couple examples for this, and then we're going to talk about the root test. So let's start with something simple, something of the form n equals 1 to infinity of, say, 2 to the n over n. All right, so something like this, well, 2 to the n, you say, well, that's very likely going to diverge. Yeah, that's a bad one. Well, it doesn't matter. Let's compute the limit anyway, see what we get. But you're dividing by n, so you say, well, maybe it converges, but n is just the sum of the 1 over n's diverges already. So by the comparison test, you could already get that this one will diverge. But let's apply our limit comparison test. It's funny when I write an example and then I myself chastise myself for writing an example that was not as exciting as I thought it was gonna be. Oh well, that's me. Anyway, so limit as n goes to infinity, and you're gonna do your 2 to the n plus 1. So I'm gonna put n plus 1 over n plus 1. And now some people, instead of just dividing by 2 to the n over n, what people do, and I think is much more space efficient, they multiply right away by the reciprocal of the nth term. So instead of dividing by the nth term, they divide, or they multiply times the reciprocal rather. And that makes your limit easier to write because you don't have fraction over a fraction, which is kind of annoying. But in this case, then you get the limit as n goes to infinity, and let's see what all cancels. So you're going to have 2 to the n plus 1. You can write that as 2 to the 2 times 2 to the n. Then you add the exponents, right? And then let's move the 2 to the n down here, and I'm going to move the 2 to the n minus 1. So I just exchanged the denominators to make it look a little bit prettier. Just comparing things that are like term to like term. So when you compare, whenever you multiply and divide there, you cancel the 2 to the n. So you're going to have a 2 that comes out. And then you're going to have the limit. These are all positive numbers. So limit as n goes to infinity of n over n plus 1. And now you remember that you have a rational expression that has degree 1 and 1. in the numerator and denominator respectively. Therefore, the limit is just the ratio of the coefficients, 1 over 1, which is going to be 1. So this limit is 2, which happens to be greater than 1. So the ratio test, you're in case 3 in part 3 of the test. So the series diverges. Series? What am I calling Siri? Series. Oh, that's funny. If you listen to this, would Siri activate? Anyways, series diverges. So that's one example. Let's do another one. Let's try one that where things will actually converge. Let's see. So let's take a look at this sum from n equals 1 to infinity. And let me think for one. I couldn't come up with anything too fun, but let's do 1 over n factorial, for example. We haven't done factorials, and for those of you who have done no factorials at all, I'll remind you that n factorial is going to be n times n minus 1 times n minus 2, and I continue like that until you get to 1. We define, by the way, 0 factorial to be 1, and 1 factorial is obviously 1 as well, because it would be 1 times 0, but you stop at 1. So we define those, and then n factorial then is defined like that, the product of all the numbers all the way up to n. So just to be sure, so when n is equal to 1, you get 1 over 1. When n is 2, sorry, you get 1 times 2. When n is 3, you get 1 times 2 times 3. And you get the idea. 1 times 2 times 3, times not plus, times 3 times 4. And you keep going like that. All right, so we're going to do our row will be the limit as n goes to infinity. And I'm going to do the absolute value of 1 over, I'm going to plug n plus 1 factorial. And then times the reciprocal of 1 over n factorial, which is n factorial over 1. So the limit I want is going to be the limit as n goes to infinity of n factorial over n plus 1 factorial. And these factorials are going to be very important. That's why we're introducing them right now. We're going to be using them when we do power series and all the actual goal of this section, so, or this whole chapter. So anyway, so what does this look like? Well, you have n times n minus 1. I'm not going to have room to write it there, am I? Let's move it. There, much better. And so we're going to have n times n minus 1, n minus 2, and I continue like that until you get to 1. Now for the n plus 1 factorial, you're going to have n plus 1 times n minus 1, and you're going to keep going down n minus 2, and you're going to multiply all the way to 1. You see, all the numbers all the way up to n minus 2, in fact, all the way to n minus 1, are going to be there, so they will be canceling. Then the n minus 1 will cancel. The n, in fact, will cancel. So you're going to end up with the limit as n goes to infinity, whatever that was, goes to infinity, of 1 over n plus 1. And this is just a rational expression where the polynomial in the numerator is degree 0, the polynomial in the denominator is degree 1, so the limit is going to be 0. So that tells us by part 1 of the criterion for the ratio test that this series diverges. Oh, converges, absolutely. What was that? Converges, absolutely. I don't know where the diverges came from, but definitely wrong. Converges, absolutely. All right, so all those are going to be more or less the same. The limits will vary quite a bit, and you're going to have to deal with factorials. Now, ratio test is especially good at dealing with powers and factorials. However, if you only have powers, the best test that you can do, or powers of n rather, not just any power, but powers of n, the best test you can do is called the root test, because you're going to be doing the nth root test, if you will. So let's write nth root test. So now the row is defined as the limit as n goes to infinity of the nth root of row of a sub n. And the conditions and the uh, uh, conclusions you get are the same. So if you're 0 less or equal than row less than 1, then you have that the series converges absolutely, just as before. Not gonna write it all. 2 row equals to 1, not conclusive, so let's put a question mark for that. And 3 row greater than 1, it tells you greater than 0. I say one thing and I write a different one. Greater than 1 means that the series diverges. So the same conclusions for the value of row. So that is quite nice because then you're not going to get messed up trying to remember, well, for this test, what did it mean? For that test, what did it mean? No, it's the same thing. So let's do a couple of quick examples. So let's grab, so at the moment I'm going to do something completely silly, but let's do it just because. So the first one, let's do n equals 1 to infinity of something like n plus 1 over 2n plus 2. I don't know, plus 3 maybe would have been nicer. Whatever. Oh, that one is actually, no, that's silly. It just gives you 1/2 plus 3, so you cannot factor it. To the end, something very, very silly. I mean, if it would have been the 2n plus 2, I would have canceled the ends and I would have 1/2 to the n, and I would have been convergent by the simply by the geometric series test. So let's just do this one where very artificial problem, but I'm just trying to come up with something quick to give you an idea how to use it only. So again, this one is much easier because you're going to be doing the nth root of n plus 1 over 2n plus 3 to the nth, and then the n and the n. And remember, there's absolute value here, so you can cancel your root and the power with impunity, even regardless whether n is even or odd. So you don't have to worry about that because there's an absolute value, and that's great because then this limit becomes the limit as n goes to infinity of n plus 1 over 2n plus 3. And that limit, same degree now, numerator and denominator, and so you just get the ratio of the coefficient, which is 1/2, which is less than 1. Therefore the test tells you that the series converges absolutely. All right, so that one was easy. Let's do one more. Let's try to think of something a little bit more exciting than that. Let's see how we do. All right, this is as good as I could think of. So I actually helped myself with the book, and I was like, okay, let's modify it slightly. All right, so this one, just for the intro, the reason why I'm not very giving you really great examples, because the root test, you kind of want to have a root or a power of n. Now you can consider things like n to the 1 over n, and do the limit as n goes to infinity. You have to do this by logarithmic differentiation. So you call this y, and then you do the natural log of y would be differentiation. Did I say the taking the limit of the natural log? Sorry, my bad. The limit and the natural log, you can exchange them by the continuity of the natural log. So you can write limit as n goes to infinity of the natural log of n to the 1 over n. So you can drop that one, and you can do limit as n goes to infinity of 1 over n natural log of n, or just natural log of n over n. And then you can do L'Hopital's here, because as n goes to infinity, natural log goes to infinity, n goes to infinity. So L'Hopital's tells you this is going to be the limit as n goes to infinity of 1 over n over 1, which is going to be 0. But that's not your limit. The limit you wanted is y. So if the natural log of y is 0, y is e to the 0. So y is e to the 0, which is 1. So you can do things like that. And of course, if it's just n to 1 over n, then the root test doesn't give you anything. But if you had something like n over, say, e to the n, or something like that, when you do your nth root, then the limit of the numerator would give you a 1, but the limit in the denominator when you do the nth root is just e, because you get e to the n to the 1 over n, and then that would give you e. So the limit would be 1 over e, which is less than 1, so this thing would converge. So you can still, so keep this one in your pocket, because it may be useful for the root test. Anyways, I got a little bit of target or of topic there, but you can use the root test for things that are not specifically a perfect power of n, but usually at that point it's probably a little bit easier to just do your ratio test. I prefer the ratio test. The root test is a crowd favorite because it's easier to do. Whenever it's useful, it's a lot easier to do. So you're gonna do the nth root, absolute value of the nth root of 1 over pi plus 1 over n to the n, and the nth root and the nth power cancel, and you get the limit as n goes to infinity of 1 over pi plus 1 over n. And then you notice that as n goes to infinity, 1 over n goes to 0. This gives you 1 over pi, which is less than 1, because 1 over pi is less than 1/3, less than 1. So then this series converges. So this is not quite a geometric series, because you have that 1 over n added, but almost, right? So the series converges absolutely. So this section is going to be a lot of L'Hopitals or a lot of limits, but the ones that are going to be a little bit different that you have to think a little bit through are going to be the factorials, but everything else is powers and things you're used to working with. Anyways, if you have questions, let me know. But I think this is good for this video, so I'll wrap it up here, and I thank you for watching, and I'll see you next time.